Okay, so I would like to make an announcement concerning the afternoon. We're going to the museum at 4. There will be a tour from, for about 1.5 hours. It's highly recommended. So, I suggest you don't skip it. The timetable is that there will be a bus going at 3:30 from the hotel where some of you are staying, the Jerusalem Garden. So at 3:30 the bus will leave from there. 3:45 the bus will come to the entrance of the campus just outside here. So those who are not coming from there can take the bus over there. At 4 it will be, this is more or less when we will get to the museum.
So leave at 4:02. If you leave at 4:02?
Yeah, 3:45 is usually 3:45.
No, but it was
usually, regardless of
I was unclear if that's when it arrived or that's when all the people who are not on the bus should leave in order to catch the bus.
The people who are not on the bus should be here before 3:45 in order to
now even I can
some The distances, just to let you know, the distances are such that actually you can walk from here to here in less than 15 minutes and from here to here in less than 15 minutes. So you can bypass this causality problem by running and walking.
If you miss the bus, just walk there. It's really close.
Okay, so we begin the next session with Stephanie Kumosa. We'll talk on TDs and X-rays and the purposes of the emission line, early detection, and most recent discovery.
Actually, sorry.
It's just
And where is the microphone?
It's working.
Okay, so I'm going to talk about some early and some recent results on tidal disruption events and X-rays and in reprocessed optical emission lines. So tidal disruption was first predicted based on theoretical considerations in the 1970s. Then in the 1980s, a major question in extragalactic astrophysics was whether there is a supermassive black hole at the center of every galaxy. And it was Martin Rees who suggested and advertised the idea to use the distinctive manifestation of tidal disruption events in form of the luminous accretion flares to search for the presence of these supermassive black holes at the cores of quiescent galaxies. And he predicted these events to look like luminous EUV to soft X-ray flares with quasar-type luminosities, but from the centers of otherwise quiescent galaxies who are in principle easily identifiable. And an early experiment which was well suited to search for these events was the soft X-ray mission ROSAT, which in particular in the early 90s carried out an all-sky survey in soft X-rays. So a number of events were detected with ROSAT, and let me just briefly summarize or show you the properties of two of these events which actually matched very well the key predictions, the order of magnitude predictions from tidal disruption theory at that time. So here you see one of the X-ray light curves of one of these events, bright during the ROSAT all-sky survey, then it faded away strongly. These first observations were covered by about a week, and the source showed a rise to an observed high state. At low state, deep Chandra follow-up observations were carried out, and you see that most of the X-rays now come from extended emission from the host galaxy. At maximum, from the very center, there's still 3 photons left, which could be linked to any nuclear emission, implying a very high amplitude of variability. Now this is how the host galaxy of this event looks like. It's a giant barred spiral galaxy at redshift 0.01. So it's the second nearest TDE. The nearest one had been identified in X-rays later. And its optical spectrum is that of an H2 type galaxy with emission lines but no strong AGN continuum. However, in the very core, there is some excess O3 emission, faint O3 emission, which might have been excited by the flare and which was seen with HST. The second event is this one, XJ1242, which again faded away strongly and is no longer detected in the deepest X-ray follow-up observations with Chandra. This arises from the core of a galaxy, from the central region of a galaxy in interacting system. And here you can see the host spectrum. This galaxy is a completely quiescent, inactive galaxy with no emission lines detected at all, neither in ground-based spectra nor in sensitive follow-up HST observations. The decline of the light curve is consistent with a T to the minus 5/3 as predicted at that time by Martin Rees, and with some evidence for a drop before the early phase decline law at late times after about 10 years. So here's some numbers. The peak, the bolometric peak luminosity was quite high, in this case larger than about 10 to the 45 ergs per second. The drop in luminosity was huge, larger than a factor 1,500. And these X-rays come are consistent with rising from the core region and rise from the inactive galaxy. Now these observations very nicely match the order of magnitude predictions by Martin Rees at that time, who predicted, the key expectations are we should see a luminous flare which declines with a sharp rise. We didn't have tight constraints on the rise phase, but then a decline on the timescale of months to years, possibly following this law. He also predicted a late time drop beyond this early decline law when the equation changes to different modes. Of course, they should arise in most of the cases from the very centers of quiescent inactive host galaxies. A simple black body estimation of the expected spectrum between the tidal radius and 3RS gives temperatures like this, which peak in the EUV to soft X-rays, again very well consistent with the temperatures initially seen. There was no prediction for the X-ray spectral evolution. What we do see in the X-ray spectra is a hardening with time, possibly linked to the emergence of a power law component, which was not there initially. NGC 5905 was also followed up in radio. This was the first one identified with Rosat. So we wanted to know whether possibly a peculiar blazar could hide at the nucleus of this H2 type galaxy, which could have done some giant flaring, which was unlikely given its optical spectrum, but nevertheless it was important to check. Also, we wondered, is a jet produced along with the accretion flare? No radio emission was detected 6 years after the X-ray peak. Now there's a number of ongoing searches for tidal disruption events in soft X-rays. One dedicated search based on the XMM Luton Sleuth survey in comparison with the existing ROSA database to identify new bright X-ray TDEs. Richard will talk about that. There's also a dedicated search in clusters of galaxies, which like Peter will talk about, and a search based on the XMM, the archival XMM database, and a few serendipitous detections have been reported. Just to show you one of the most recently published soft X-ray TDEs. It was detected with XMM by chance in a pointing. It was found in a search for highly variable X-ray sources in the XMM Newton database. It has a very soft spectrum of temperature about 0.1 keV, possibly subject to a fast-moving warm absorber. Fortunately, there only exists this one high-state data point. Further pointings, which by chance still included the source, only provided upper limits, so the X-rays declined strongly by at least a factor of 260. However, the fact that the peak luminosity is very high, just in the X-ray band itself, 5 × 10⁻43 ergs per second. And the ultra-soft spectrum and the fact that this flare arose from within the central region of an inactive galaxy, so not an AGN, an inactive galaxy, make this another nice tidal disruption candidate. So here's a distribution of the peak luminosities of the X-ray detected TDEs, of the soft X-ray detected TDEs. And this is just the observed peaks and in the narrow 0.1 to 2 keV band. So these are safe lower limits to the actual volumetric luminosity observed. They range between on the order of 10⁻42 to a few times 10⁻44 ergs per second. Then just here shown, for example, for NGC 5905, these X-ray spectra were very soft, and we were very conservative in estimating the lowest possible seen luminosity, which is not allowing for any excess absorption in the host galaxy of the flare. If you add a bit of absorption, then you increase the intrinsic X-ray luminosity, and of course we did not catch these events exactly at the peak, and there has to be a volumetric correction, so typically the events might be more luminous by a factor of about 10. Now here's a summary of the published cases of TDEs or candidates as of early 2015. This includes all the sources which varied by at least a factor of 2 and up to, in the most extreme cases, around a factor of 10,000. And it includes those cases which have a host galaxy spectrum for assessment, that it is either a completely non-active galaxy, a quiescent galaxy, or that it is only mildly active. There's a number of, or at first the majority of events had been identified in X-rays. There's a number of UV events, and recently in particular a number of optical events have emerged. We've heard yesterday that the first event was a broad helium-2 emission line was 10JH, but that there were previous detections which nobody knew about. So let me talk a little more about these events, which were first identified from the Sloan Digital Sky Survey in the optical. They were noticed for their very strong ion emission. They do have broad Balmer and helium lines too, but also a host of other emission lines. So if you first have a look at this spectrum shown in orange, this is the initial SDSS spectrum, which we noticed in the SDSS archive, searching very generally for peculiar emission line galaxies. And what is so remarkable about this SDSS spectrum is that the high ionization lines like ion 10, ion 14 are almost as strong as oxygen-3 emission. So in terms of ion over oxygen ratio, this is one of the most extreme emitters in the SDSS database. And in particular, in order to see, simultaneous X-ray observations do not exist, but in order to see these highly ionized ions, which do have their ionization potentials in the soft X-ray regime, you need to have a strong X-ray continuum to produce these ions, which are necessary to create these lines. So we immediately checked the ROSA database whether there was an X-ray detection of the source, but there wasn't. Also there's strong helium-2 emission, broad helium-2 emission. There's broad Balmer, hydrogen Balmer lines with red asymmetric profile, and the helium-2 and Balmer lines also keep fading. We did follow-up observations with Spitzer, hoping that maybe in the mid-infrared we would see some high ionization lines too and could follow their evolution. None were detected, but with Spitzer we did see luminous mid-infrared emission. Follow-up observations with Chandra showed, however, that the source about 3 years after the SDSS high state was much fainter in X-rays. Now, when we noticed this system in the SDS archive a few days later, we got a first follow-up optical spectrum, because the quick question was, are these high ionization lines permanent, or are they possibly transient and excited by a luminous flare? And now here you see the first follow-up spectrum, which was taken at the Qinglong 2-meter telescope. And as you can see, the emission lines faded. In particular, the highest ionization ion lines are completely gone, have faded by more than a factor of 2 and 3 years. Now, what kind of galaxy is the host galaxy? Is this an active or non-active galaxy? We cannot tell with 100% certainty, because usually one of the major classification schemes uses optical emission lines because they vary. Any diagnostic classification comes with some uncertainty. Nevertheless, if you take the low ionization lines, put them in diagnostic diagrams, this is between LINA and H2 region. This is not a classical permanent AGN. So the X-rays are faint. There's no radio detection. In the optical low state spectrum, there's no evidence any longer for any faint optical power law emission. We just see the host galaxy. The iris galaxy, the iris colors indicate a relatively inactive galaxy. The black hole mass we could estimate from stellar velocity dispersion measurements, which is on the order of a few times 10 to the 6 solar masses. It's not completely gone. It's fainter. I'll show you. I'll show you in a second. So these observations imply that a luminous EUV to soft X-ray flare must have occurred. It was not observed directly because there was no simultaneous X-ray observations, but we do see about a factor of 2 variability in the NUV, near UV to near infrared continuum, and we see this broad and narrow emission lines. And now you see in much higher detail, actually I did not overplot the second spectrum, but the broad H alpha, it faints. It gets fainter by about a factor of 2. It's not completely gone in the first follow-up observations. So you see a zoom on the H alpha high state profile seen with SDSS. It's red asymmetric strong Balmer line. It has some extra peculiar narrow unresolved features which do not occur in any other emission lines. The same for H beta. So there's strong helium-2 in high state, which also fades. So we wondered, because there's no strong evidence for permanent AGN, did we see the emission line reprocessing from a tidal disruption event, illuminating the surrounding interstellar medium? So clearly this event must have occurred in a gas-rich galaxy, where the narrow lines come from the surrounding gas, but the broad lines might be linked in one way or another to the stellar material. However, I always worried, and I still wonder about all these optical transient emission lines. How safely can we really exclude a peculiar supernova? In this particular case, if all of this was due to supernova, it would be one of the most luminous known in several respects. In particular, these very strong iron coronal lines are very unusual. Just a few supernovae do have these lines detected, and this case is a factor of 100 to 10,000 more luminous than the few iron coronal line luminous supernovae. So we then carried out a more systematic search in the SDSS database to find more of these events. So the key criteria were to detect strong ion emission, ion coronal emission, and that the first follow-up optical spectroscopy showed that these lines were not permanent but faded. So we found 3 more good cases with fading ion lines, while oxygen seems to increase with time. All of them come from the very cores of their host galaxies. The host galaxies show H2 type emission line spectra, except for the high ionization component, and all of them are relatively low mass based from the fact that the absorption lines seen in the optical host spectra are no longer resolved with SDSS. So the overall similarity of their spectra suggests similar mechanism at work, and a very rough estimate based on the number of sources which were emission line galaxies which were looked at with SDSS. The rate is about this. So how much time do I have? Okay. So briefly, let me spend the last few minutes in addressing the question, what about tidal disruption events in active galaxies? So when we searched for the first events, it was very important that these happened in quiescent galaxies to make the point we actually see tidal disruption events rather than variability related to the accretion disk, which is permanently present in AGN And so many AGN do vary in X-rays. Now, all the first cases I showed you identified in soft X-rays, they are quiescent, and the amplitude of variability, the drop in luminosity, is so high that it's much higher than observed in any known AGN. But again, now we can look at active galaxies and ask, do we detect tidal disruption events in active galaxies? How do they look like? How certain are we about their classification? And there's one very peculiar Cepheid galaxy called IC3599, which was first noticed in the Wizard All-Sky survey as one of the most variable AGN. It was first bright in X-rays, but then when followed up again a year later, it had faded by about a factor of 60 and continued to fade a little further. So at that time, a few outburst mechanisms were considered, in particular that we had an extreme case of X-ray variability in a Neverland Cepheid 1 galaxy, whatever the mechanism to drive it, possibly a TDE or perhaps some kind of accretion disk instability in this AGN. None of the possibilities were explored rigorously, all of them were mentioned. And at that time, in particular, when Martin Rees was asked about his comment about the system, whether it could be a TDE, he said he would like to see these events in quiescent non-active galaxies to be sure that we don't see anything related to a permanent accretion disk, which has some permanent luminosity outputs, which makes the AGN typical Neverlines. Now, interestingly, recently, IC3599 flared again with Swift. It was seen in other X-ray high state, which was at maximum almost as bright as the initial Wizard high state. Fortunately, we only noticed it a few years later and then did a number of follow-up Swift observations which showed that the source was then faint again. This is with Swift spectra in the optical, UV, and soft X-rays. You can see that also the optical and UV varies, but the highest amplitude of variability is seen in X-rays. We also found a Catalina optical All-Sky server light curve, which shows that the optical was bright already about 2 years earlier than the Swift X-ray and optical high state. And so what did happen in this galaxy? Well, the fact that it is a classical AGN, and in particular that the classical tidal disruption flares were not expected to flare again, then strongly points to variable AGN scenarios, possibly some kind of instability in the accretion disk. At least the amplitude is still quite high in comparison to other AGN, the amplitude of variability of a factor 100. However, we can now also consider variants of tidal disruption events which do predict repeat events. For instance, it has been predicted that the tidal disruption rate can be strongly boosted when you have a galaxy merger, or perhaps in the early phase of a recoil event. Optimistic predictions by Chen et al. Predicted the rate as high as about 1 event every 1 to 10 years. So maybe we are just seeing this. However, the host galaxy does not show any indications that it's ongoing, that we have an ongoing merger. Now, if we have a TDE in a binary supermassive black hole, the action of the binary temporarily interrupts the accretion stream on one of the black holes. So we have a light curve that does not smoothly decline, but that shows some quite erratic flaring. However, the second peak, 20 years after the first one, was as bright as the first one, and so this is an unlikely scenario. Campana et al. Recently, in application to I3599, suggested we might be seeing a tidal stripping event, and Ilya Mandel recently predicted, not explicitly in application to I3599, but as a general idea, that if you have a binary star in a single supermassive black hole, that might be disrupted and could produce a second flare. In that case, we don't expect a staggered peak. And just recently, we saw I3599 going into possibly going into a third high state, where the optical is already as bright again as in the previous high states. So, in summary, soft X-ray TDEs have first been found with Rosat. They very well matched all the order of magnitude predictions from tidal disruption theory, and they are from quiescent galaxies and show very high amplitudes of variability. I didn't talk about Jeter TDEs first found with Swift. We'll hear about more of them later. Then emission line TDE candidates. based on their broad and narrow emission lines were first identified from SDSS. And these were expected if a luminous accretion flare explores in a gas-rich environment. Okay, and there's some interesting future applications I put here. So thanks for your attention.
Very simple question.
Yeah.
You showed us a slide a couple minutes ago with the IP3599 spectrum. It was on the screen for about 5 seconds. Can you show this to me?
Yes, yes.
There. We went that way. For the broadband spectrum.
Oops, let me see. No, yes, this one.
Okay. Okay, thank you.
So these corona lines like echoes, I think are very interesting. Actually, I've been observing the galaxies where we've seen the optical UV events, going back to them after a few years to see if maybe they developed these corona lines a few years after we saw the optical event. Is there a sense of where this gas is and what kind of time delays are expected between the two and these?
I guess it depends on the sort of on the gaseous distribution in the environment of the core.
Right.
So it could typically be high density gas, say some parsec away. So yes, or closer. So yeah, so a few years. So the light travel along our line of sight might reach these clouds early, and then you have with some light travel time delay, you reach further of this gas.
So it does make sense a few years after the science developed.
No, a few years, absolutely, yes, because of light travel time delays. You know, whenever the luminous flare reaches some say a molecular cloud, some dense gaseous material, you do expect some reprocessing and to see these lines.
Yeah, so in addition, building up that question, given the time scale to observe these galaxies, is it conceivable that you could actually visually resolve echoes or any object?
Yeah, so it would have been great to have better spectroscopic coverage. Let me see, the database we have is the first SDSS spectrum, but we only noticed it 3 years later than it was taken, because then it entered the archive. And so the first optical follow-up spectrum is 3 years later, and then we can see that there's strong changes where we do not have any reverberation mapping. And then we have another one another year later, and this trend is that the low ionization lines, the 3 gets a bit stronger, the highest ionization lines fade further. But the time sequence of the spectra is not enough to do reverberation mapping. However, it would be a great way. You know, there's this classical reverberation mapping in classical AGN of the broadline region. Now, these tile disruption events, you have an idealized situation of just one single giant flare, which then travels through the core of the host galaxy, and whenever it encounters some material, it's being reprocessed. So there's a lot of future potential.
I'm thinking less of reverberation mapping and more of like light echo.
So the very, very closest subject, like, would go over to 20 megavolts, then after 10 years or so, it's like millioptic. So it would be possible maybe with
Okay, you think of spatially resolving it directly. Yeah.
I guess you showed the Catalina sky survey. Did I understand right that was between the two X-ray flares? And now the
Yes,
third flare is
yes, indeed. So this zooms now on the second flare. This is the Swift high state in X-rays, and the Swift UV high state with Catalina. You confirm that high state, but you show that it, at least in the optical, it has been on already earlier, about 2 years earlier. So this covers a time span of 2 years.
But we don't know what the X-ray may have been.
No, unfortunately not. We only have this Swift data point.
Recently you showed that it was coming up both.
Yes. Okay. Yeah, I was running out of time a bit, so let me just. So very interestingly, just recently in August this year, we saw that the optical was already bright again. The UV was a bit higher, but the X-rays were not yet. So unfortunately, then the source went into sun constraint. We could not follow it up further. but just last weekend we had it was out of sun constraint, immediately Swift took a new observation, and the optical is still high and the X-rays are still low. So if this is the onset of a new major flare, it means that the optical comes first, but we have to see how the light curve develops.
On the X-ray, there's an upper limit just before the second flare. Where was that chronologically relative to the optical problem Catalina data?
Let me just check. So the upper limit is, I think, from the XMM slew survey, and I think that was before the Catalina. Oops.
One more question and then we'll check.
How much of a missing energy problem is there in the X-ray selected TV sample? You showed some photometric corrected luminosities at the beginning, which were pretty high. So I guess how trustworthy are those photometric?
No, volumetric corrections are uncertain. So the safest one, we have the measurement in the soft X-rays, and we can play a little bit with the absorption. You know, if you lower a bit of absorption in the host galaxy, not dramatic, but just what we see in our galaxy, because this very soft X-ray event, you boost it a little bit. But then in order to go to the volumetric correction, they can be a factor of a few, or they can be higher. So this is uncertain. We do not have any simultaneous UV observations of these first events to get the broadband SED.
Thank you.
Not looking good. Hey, whew, blimey. Okay. All right. Good morning. So exactly, we want to talk about the particularly the X-ray TDE, which we've found in the slew survey. So thanks to Stephanie for generally introducing X-ray tidal disruption events. So this is our slew survey. This is our basically our mechanism for detecting tidal disruption events. And what, as you can imagine, what it does is the XMM looks from one observation to another observation, keeps the cameras open, and it gets something like 10 seconds of exposure time on each particular piece of sky, which is not great, but the cameras are quite large, and so roughly it gives you the same sort of sensitivity as the ROSAT or Sky survey. And this allows you to actually do a comparison between what we see and what ROSAT saw 20 years ago, and then pick out basically anything which is brighter, any transients. There's a few flare stars, a few active AGN, but we also see tidal disruption events. And what we particularly see, because the sensitivity is not great, is we're seeing tidal disruption events which are from bright in the X-rays and from relatively nearby galaxies, in fact. Okay, so I think, as people have mentioned, there's been a bit of an explosion in the literature over the last 18 months or so. And to me, these are the four questions which have come out from that, from these papers. Is that A, why is it that, given the models, that circularization should perhaps be a bit further out than previously expected? We always see prompt, quickly rising, short plateau, quickly decaying tidal disruption events. Why do most of the tidal disruption events we see in the X-rays have soft emission and not have power laws like the AGN do? The outflows that we see, particularly from 14 Li, somebody mentioned in one of the papers that these are ubiquitous, or can we say if they're ubiquitous or not given the data? And then looking at the fact that the low temperature optical events is the fact that could this be from reprocessing or not? Can we say anything from the data we've got? Okay, so the fast rise events, I mean, it's absolutely true that whether you look in the X-rays or the UV or the optical, we always see a rise which takes place over weeks, maybe a month at the latest. And then a plateau which is kind of like negligible, and then it starts to decay almost immediately. So why is this? Okay, in this particular year, then there's been several papers on this. And I think at least these 3 papers have been talking about having circularization quite close in, quite far out rather, in which case then you should be getting some sort of relatively slow infall of the material. The accretion disk extends, and so you get a relatively slow rise to peak. The material is extended, so you get more material accreting more slowly, so you should have more of a plateau before it then joins off on the t to the minus 5/3 as before. Thanks for the plot. So fine, and I particularly like this phrase in James and Enrico's paper saying that probably we don't see this because it's a selection effect. And in an optical, maybe it is, because in the optical then you're certainly seeing, you're looking for very sharp rises in the flux. But in the X-rays, we've got this 20-year baseline between what ROSAT sees and what we see, in which case there's absolutely no bias at all now. So we should be seeing what is really out there. So, okay, this is the first ever source that we saw, and I think it still holds the record for the closest source at about 20 megaparsecs. It's a typical tidal disruption event as far as the X-rays are concerned anyway. Falls off quite nicely as t to the minus 5/3. It's got a temperature of 80 eV or so if you fit it as a single black body. And when you look at the optical spectrum, then there are sort of emission lines, but at a very, very low level, so that you can constrain any sort of persistent AGN to below 10 to the 40, let's say. So which is a couple of orders of magnitude below the peak luminosity that we see. Now, that's fine and everything's consistent, except for we did some change to the processing software which allowed us to look at some very early slews. And then one of these slews showed that there's actually the peak flux was already there 18 months beforehand, in which case, because you've got this quite nice t to the minus 5/3, then it's very difficult to then put it here. You go up too fast basically. So there's no way that this is on a part of a standard curve, and then this then looks like you're on a rather flat plateau type area for 18 months or so, which looks much more like the sort of light curves that these late circularizations are predicting. However, we discovered this before all those papers came out, and so when I saw this I started reinterpreting it as an AGN event, in fact. So with AGNs, I mean, all this soft emission comes from right close in, okay? And like with galactic binaries, then there's the idea that for some reason then you get a hole in the middle, you haven't got any soft emission, it falls in, material falls in, you get a change in state, you've got lots of soft emission, and you get this soft flare, it goes into the soft state, let's say. But for AGN, you just don't have the time to do that. It takes like decades to do that, and to get a factor 100 rise. So what people propose in binaries as well, because they have a similar sort of problem, is that you get the viscous infall slowly, but then you have to have some sort of instability. So the material gets so compressed that the radiation pressure takes over, you get a thermal runaway of a heating wave, the material expands, you get a thicker disk, and then you can get this very large factor 100 rise in the soft flux. This material then gets relatively quickly eaten, and then it goes back to the low soft state, let's say, or back to the low hard state, in fact. So fine, I mean, just at this time, the IC359, which Stephanie talked about in detail, came along, in fact. And so then we applied this model to this second curve from IC3599, where it seems to work okay, and the timescales are so fast, in fact, that if it is an AGN, then it's got to be some mechanism like that. Now, but putting it back to NGC 3599, then because this is such a weak persistent AGN, and because we've only seen one flare from it, then I think I still prefer the explanation that this is more like a delayed TDE, or possibly because the luminosity is quite low, and it could be stripping of the atmosphere of a red giant, in fact, because we're only at 10 to the 42. So, which gives you this kind of like slower rise and long plateau. Okay, so the second question is, why isn't there power law emission? So we all know in AGN that in like 99.99% of AGN, then not only do they have some sort of thermal disk, but they also have a power law, which is supposedly thought to be by hot electrons, which are Compton upscattering, let's say, the photons. So that's fine, but in almost all of the tidal disruptions we see, then the X-rays are soft with no hint of a power law. This is the example from Linatel, where we see it's actually got 170 eV. It's quite a small black hole, but no power law. And I think this is the same for almost all of the sources that Peter Maxim has found as well, and the early ROSAT events, and most of our events. Whereas I think when you look at thousands and thousands of AGN, then there's only like 3 or 4 events which don't have power laws and do have X-rays. Okay, so there are, however, because Roland Walter in particular has been looking at the higher energies surveys, and then they're starting to find a few power laws coming in. So with the integral and the swift batch sources, and we found one last year which may be a AGN, maybe a tidal disruption event. This is actually the spectrum of it. And I think the Bradchenko source is also, although you didn't have many photons, had a relatively hard slope, let's say of 1.8 or so. Okay, so let me introduce you to the new source that we found recently. This is 2MASS X0740. We saw it with a factor 15 increase in X-ray flux above ROSAT. This here at a redshift of 0.017, and normally it wouldn't have been enough of a flare to actually cause us to monitor it. But in this particular case, then it had a 2MASS spectrum from the 2MASS redshift survey, which showed pretty clearly that it was actually an inactive galaxy. So we decided that we were going to monitor it anyway. Now, when we followed it with SWIFT, then we saw it dropped off here in the X-rays relatively rapidly, at first at least, by a factor of a few. And also in the UV filters, then we found in the end like a 3 magnitude change in the sort of short wavelength filters, and a 1 magnitude change in the long wavelength, the UW1 filter. So there's obviously something's going on here. It's pretty interesting in an inactive galaxy. And then when we looked at it with a long XMM observation, then we see in this case indeed then it does have the high energy 2 to 10 keV photons with a reasonable slope. So you can roughly fit this at least with a single black body of 80 eV or so, and a power law of a typical slope around 2. So it's quite nice. We've got lots of flux, so we can investigate this now. So when we look at the actual light curve in the various different bands, and in the 2 to 10 keV band it's falling off it's falling off anyway over 500 days. The soft X-ray flux is doing something similar, although in detail it's a bit different, and the UV filters are falling off a little bit slower. So It's not actually t to the -5/3, and in fact we get a slope of about -1 in the X-rays and -0.5 or so in the UV. But nevertheless, I think it's looking like a definite tidal disruption event at this stage anyway. Now this is one of the things where we get the UV filters and we get the soft X-rays, and you can actually connect them very, very nicely. We've got quite good data here. And so using a multicolor Dis model, which we tend to use this Optex AGN model which Chris Dunn produced, which has got multicolor thin disk with the Novikov Thorn emissivity profile. And then you can, without any tricks or renormalizing, just with the standard reddening at the optical and the galactic NH, nothing else, then you can get these points to fit immediately. This gives you a very good handle on the black hole mass, if you assume that what the spin is. So with a spin of 0, then we get a reasonably tight constraint of 2 × 10⁶ solar masses for the black hole, which from the luminosity is giving us a Edding ratio of about 0.1. This is already a factor 10 down on what we saw at the peak, so that means that at peak at least the Eddington ratio is going to be about 1, so Eddington limited probably. Of course, if you have a higher spin, then this allows you, as we saw in Jane Dye's talk, to go to higher masses. But of course we've got absolutely no constraints on that at the moment. Now another thing is that if you look at this as the short-term light curve, this is views of 10,000 seconds, and we see factor 5 variability in the soft X-rays on these sort of time scales, and a doubling time of something like 400 seconds. So by the standard arguments, then this also tells you that the black hole mass is just a few times 10⁶ or so. So this is looking all fairly consistent. You may notice, or you probably can't, that at the higher energies there's a little bit of a problem with the fitting. And so in fact, if we look at it here, then although we can fit it broadly, the X-rays with a multicolor multicolor black body at the low energies and then a parallel at the high energies, it doesn't actually fit perfectly, and there's some sort of excess here, let's say. Now it's very tempting to put that excess as reflection. I mean, obviously we've got the parallel, we've got lots of material in the middle. You might expect to see some sort of MCG 630 reflection from the middle, either with narrow lines or with broad lines. But we have the same problem as the AGN people, in fact, is that you can fit this equally well by changing the absorption or by putting in emission. So we'll do it the easy way and we'll put in absorption, and so if you fit this with an absorber, then you've got something like 10 to the 23 of material coming off, covering factors of 80% or so, but it has to be reasonably highly ionized because you've got no absorption lines at the soft energies, so you've got absorption of 2 or so. Okay, better move on a bit. The second observation is showing you that when he comes down, it's quite interesting really, because the soft X-rays have changed enormously from one observation to the second one, which is 300 days later. But the medium energies 1 to 3 keV haven't changed at all, at least in flux. And then this excess seems to have gone away a bit. So it's perfectly reasonable that the emission from the thermal component has died away, which gives you the change here. Exactly what's happening at the high energies, we're not sure. It could be a change in absorption, or maybe the parallel slopes change, which would also give you this effect. So the modelling at the moment is ambiguous, and we need to work on it a bit more, I guess. Okay, so we took an optical spectrum 30 days later, which doesn't show any broad lines, and confirms that it's not an AGN of any sort. Right, so ubiquitous absorption. Just like to have a quick look at this, and not got time really to go into it, but I mean, I was extremely sceptical when I saw that. But actually thinking about all the AGNs, all the X-ray TDE that we've seen, we can't say that there's anyone which doesn't show absorption. So it's quite possible that there are outflows from all of these sources. And I can't find an example which which shows that there isn't in any particular cases. Okay, so finally, looking at this, the idea that the optical emission is caused by outflows which are then reprocessed in this UV X-ray disk emission. I mean, it's a nice idea, and so I thought I'd look at all the sources which we actually got in the literature which have had multi-wavelength coverage, and there's actually not so many of them, probably only about 10 or so. Now, the ones which I've got good optical, no, let's say they've got an optical flare, but they don't have an X-ray flare at all, are these two, I believe. So in this particular case, these two do agree, let's say, with that scenario. But then there's these 4 sources where you've got your optical flare, which is certainly at a few times 10 to the 4K, but then you do have an X-ray flare as well. Although at least in one of these cases, then there's the strong absorption, and the others it's just not known because the X-ray spectrum wasn't good enough to say. So whether this now can start putting any sort of constraints on the covering fraction, let's say, of the reprocessor, and whether we've got the absorption which is killing off the X-rays in the line of sight, probably there's still not enough statistics, but at least in sources like this, then I think we can start to look at those sort of models anyway, to see if that's a plausible scenario or not. I guess I'm out of time now, so okay, thank you very much. Of
the distal mass also.
Yeah. Oh, sugar. Come in. Yep. Yeah, okay.
Yeah, my question was also about the spectrum. So it seems like there's nothing happening with respect to the host, even though in Swift UVLT you do see.
Yeah, okay, fine. So it's true, but I think that's just an extension of the hot the hot accretion disk. So by the time you go down to the U filter, then the change is only half a magnitude, and in the B filter it's like 0.1 magnitude or something. So I think you're really absolutely not seeing any optical change at all. There's no optical flare basically. Yeah.
Well, that really argues against reprocessing because that is predicted to go all the way down to the optical, whereas this is
right.
So you're saying you can fit the UV and soft X-ray with the multi-component.
Yeah. There's no need for any optical. Sure.
The last picture,
Let's see, where's the... Which one of these do I use? This? Happy Halloween. All right, so the title and abstract of this talk is at least slightly purposefully vague because of the new Assassin 14LI result, which was A, not public, and B, there are lots of other people who have been working on it, and I'm not the spokesman for the group or anything like that. I just think that it's extremely interesting and would like to include it in my talk. So I will at least cover that somewhat in detail. Mike? Oh. This is it. This is a tiny microphone. Okay, is that better? Okay. Yes, so a lot of what we're used to dealing with in X-ray astronomy is basically CCD spectroscopy from events discovered in imaging through archival surveys or what is going on here? No, it's not. Might be the refresh rate. Okay.
Oh, it's okay now. Just
okay. Okay. It likes my display window, but it doesn't like the... Okay. All right. So as Richard said, typically we try and fit these things to just a black body or maybe a really soft, powerful... This is really weird. Does anybody have a good sense of why Max might do this? No. Okay. Yes. So oftentimes, if you have photons, which, as we've seen, some of these events don't have any, the best you can typically do is fit either a black body or a soft power law. The top example is from my 2013 paper detailing a flare from an intermediate mass black hole in Abell 1795. There's 750 counts in the brightest spectrum there with the red diamonds on top. And there may well be some structure in there, but even then you're kind of reluctant to throw a line or an absorber into the model just because it's hard to say how significant it will actually be. The bottom one is from RBS 1032, which is another archival example of a tidal disruption flare in a dwarf galaxy, which was originally attributed to being a star before it was reviewed by the Sloan Digital Sky Survey, reviewed in the Sloan Digital Sky Survey by Gaush et al. And determined to be a galaxy with some sort of emission, possibly from an intermediate mass black hole. But there was a significant decay over the course of the 15 years or so from the ROSAT All-Sky Survey to 2009 follow-up XMM observation. And again, you have something that can basically be fit to a power law or a black body. And I don't want to go into that result into too much detail because it's been out for a little while now, but I'd like to reemphasize the fact that we are finding occasionally things that were previously not thought to be tidal disruption flares in the ROSAT All-Sky Survey should serve as a word of caution for interpreting results on the tidal disruption rate from that survey. A lot of people like to cite the Donnelly 2002 paper inferring a disruption rate of 10 to the minus 5 per galaxy per year. Between this result and another more systematic survey by, I think, Kababuan and Sazonov, it's clear that it's possible to find things that just hadn't turned up if you are a little more flexible with your interpretations of what the light curves should be like. And the disruption rate, I would say, is probably at least a factor of a few higher than that, just from a very, very rough estimate. Now, the limits of what you can get from CCDs are, we're starting to see some fairly interesting and useful results. Richard and Stephanie talked about Da-Cheng Lin's recent study of an XMM catalog source from 2000 that appears to have an edge attached to it. I just wanted to talk about it in a little bit more detail. The bottom two panels on this plot are the residuals to the best fit continuum model. And as you can see, there's this dip here right around 0.8 keV that goes away if you fit an edge to it. The edge implies that there's some amount of absorption there. It's at about 0.85 keV, and it implies a very high ionization medium, relatively large column density, and it's also pretty well blue shifted. It's got a blue shift of about 0.1. So if you interpret that as being a warm absorber of some sort, and you can fit an absorption multiplicative component to the continuum, then that's pretty good evidence for some sort of ionized absorber outflow. Now, why do we care about edges in X-ray astronomy? Well, X-rays have a preferentially higher opacity to the inner shell electrons, and so when you have a lot of high energy electrons interacting with these with various species, you can actually have electrons that are absorbing photons from their inner shells, and you stop seeing the absorption at a very sharp point where that particular electron will be ionized. Now, in the energy range that we're looking at for most of these super soft X-ray events, one of the most important ionizing elements, one of the most important sets of species is oxygen, where you get these really prominent, this is just a model warm absorber of 10 to the 2 per square, 10 to the 22 per square centimeter. But you see very well-defined edges associated with the inner shell electrons from each of these ions of 08 and 07, and then progressively lower energies. If you get really, really great results like Richard Saxton's et al. From 2014, you can actually get a much more confident and detailed fit to your absorber. This is a neat result that shows that not only is that there's significant evolution in the behavior of the absorber over time, where the ionization goes up and the column density goes up. but it's also basically at the limits of what we can do with CCD spectrometry, because the resolution for CCD spectrometers is, the energy resolution is about 100 EV, maybe 50 EV. You can't pick out discrete absorption features very well. And the X-ray spectrum is pretty complicated in this range. Why should we care about picking out discrete absorption lines? Well, one of the fun things about X-ray spectra is that when you strip off all of your outer electrons, then the elements that you're looking at that can cause absorption or emission lines, they might have 1 or 2 electrons left, and so they can be approximated by analogies to hydrogen or helium. And so the things that we would expect to see are going to be like helium-like carbon, nitrogen, oxygen, neon. And the triplets themselves, like helium, are very good, are very highly sensitive to the density and the temperature based on whether the resonance, the intercombination of the forbidden lines are more prominent. So the state of X-ray spectroscopy about a year ago was, as far as I was concerned, mostly power laws and black bodies. And so when I gave a talk to 15 years of Chandra, one of the things that I considered a big unknown was X-ray emission lines and absorption lines and edges. There still was not a whole lot of work out there. Richard et al.'s work was still pretty new at the time. But just a few, less than a month later, the ATEL went out for Assassin 14Li. And this is an extremely exciting event for which we all owe a debt of gratitude to the Assassin team, because it's by making their notices public that people have been able to follow this up in great detail. It is, as the slide says, the closest known supermassive black hole stellar TDE in 10 years. The claim for the most recent one before that is NGC 3599, which Richard mentioned in his talk. And if the XMM sleuth survey had been in the state that it's in right now, they might have been able to actually get this sort of result with a relatively long XMM observation. This is the result of 95. There's a 95 kilosecond long stare with XMM. There's a couple of 20 kilosecond observations, and then there's a Chandra low energy transmission grading observation. With XMM, RGS is baked in the cake. Every observation has RGS, but because you need to have a certain number of photons per bin in order to describe a discrete feature, for the most part it's just not useful. It's only when you start getting 5 times 10 to the minus 12 ergs per centimeter per second, ergs per centimeter squared per second, that you actually have useful results. And so you need something really close like Assassin 14Li to do something with it in a classical non-relativistic tidal disruption flare. Now there are a whole bunch of lines that are listed here. You see 08, 07, calcium, a bunch of argon lines, sulfur 14 and 13. I'd like to draw to your attention at least a few things about the overall structure of these two results. You see the same features across spectra. When you're looking at an absorption line spectra of relatively low significance and you don't know what you should be looking for, you're skeptical of any model that you want to throw at it. And right here, these observations are taken within like a week or two of each other. And you can see basically the same features across spectra. You also see them across the 2 RGS spectrum components. So we're confident that most of these absorption lines are real. You also see some other weird emission features that are close to the absorption lines that are relatively low significance, but again, they're relatively consistent across observations. Let's pick a good one. That one's next to argon, I think. This is not a perfect fit to the spectrum. There's these pretty strong residuals, but these emission lines maybe analogous to P Cygni profiles, where you have a low density emitting component that's associated with whatever absorber is causing the lines. And I would like to at least go over the energies at which you expect to see these lines, because each of these lines is a tracer of the species that is actually emitting it. You see 07, 08, these are the ionization energies of each species. So above that, you start to see the next species, and you start to see less of the original species. So these are all relatively consistent with a photon population that's like 0.6, 0.7, maybe 0.8 keV that is exciting the absorbing medium. The medium itself is it has a relatively low filling factor. It's like 0.002. Now, from the variability of the XMM flux itself, you can set a limit to the size of the emission region, and that between that and the column density and the ionization factor, we get a sense of what the filling factor is like. And the total mass that's enclosed in the absorber is something like 10 to the minus 4 solar masses. Now, one other thing that's really weird about this absorber is that the velocities are relatively small. You're talking maybe 100 kilometers per second, a few hundred kilometers per second. This is much lower than the escape velocity from a black hole of this mass. I mean, you expect to see maybe 10,000 kilometers per second. So the question is, why do we see such a low velocity? And there are a few ideas that people have bandied about and included in the paper to explain where this may be. It might be that we're looking at some sort of projection factor where we're only seeing a preferred angle from the wind. Maybe we're actually looking at bound material. Maybe we're looking at absorption from a stream of accretion. The interpretation from the paper itself is that we are seeing a wind, and I think that's a reasonable interpretation, but there's still just a lot that we don't know about. There are a whole lot of, this is just the beginnings of what you can do with this particular spectrum. There are a whole bunch of lines that have not yet been confidently attributed to some sort of species. And there are a few that there's at least one that this model predicts that doesn't show up. It's a carbon line at about 34 angstroms. So there are enough photons here where you don't just get one X-ray spectrum from one long stare. You can slice it and dice it, and you can see how it evolves on short time scales. The velocity goes up a bit over the course of